How's it going, everyone? So, today's just going to be me programming basically. Um, I have been playing around with Falcon Virtual in production, and an implementation detail came back to haunt me a little bit. That is HTTP2 tracks a lot of state per connection. So, what that looks like, this represents a connection, and in this connection we have things like flow control, which is how many bytes we can read or write. It helps to stop connections from just overloading on slow networks. And in particular, we have these two hash tables, and this hash table is essentially every request or response that has ever been made on this connection. And this list of children is kind of the same thing, but for dependency purposes, which is kind of something specific to HTTP2. And it is essentially a way of prioritizing one stream, or like one request or response over some other request or response. It's not used very much in practice, but it is part of the specification, so it needs to be supported, of course. The main problem is, as you can imagine, keeping around every single request or response it can cause a problem for a server that is processing a lot of requests or responses. And that is quite different from HTTP1, where essentially after every request or response, you're finished. There's no further state tracked beyond like keep alive. So the problem is this is essentially using a lot of memory, and eventually it causes swapping to occur, and it's just a disaster. I mean, when you consider running on a small memory constrained server, the kind of issues you could run into. So what you kind of imagine is, within this list of streams, at some point you should be able to delete the state. And there is a certain point where I think that's possible, and that is when the stream enters the closed state. So a stream represents a single connection, a single request or response. And it has this diagram in the RFC, which I've copied into the code here because I refer to it sometimes. And essentially, every stream, even ones that you don't have in that hash table, are in the idle state. And when you receive headers, you move the stream to the open state. Then once you have, when you're in the open state, you can send and receive data on that stream, and eventually one of those data frames will have the end stream flag set. That is the equivalent of, say, a post request which has a JSON body. And so you move into like one of these half closed states, which means I'm ready to send a response back. And so then you enter this situation where you can send data back, and then you include with one of those data frames the end stream flag, or you send a stream reset frame and you enter the closed state. And it's at this point that anything that was associated with the stream is no longer required because the stream is closed, except for the priority, like the prioritization. And the reason why streams play a part in the prioritization is because streams are used as nodes in a tree, in a priority, like in a tree that specifies priorities and how you split up the available data. So let's say you have 3 streams, and normally, let's say you have 300 bytes in your window for sending data, then you might split those 300 bytes into 100 bytes for each stream. But if those streams have different priorities, then you would split that window differently. Like you might prioritize the first stream with all the data until it's finished and then split between the remaining ones, for example. So it's quite complicated that prioritization lives beyond a stream entering the closed state. So even though we're finished with this stream, it still can play a part in prioritizing other streams and flow control windows. So I was trying to figure this out, and I found I was looking at what other servers were doing. Let me see if I can find this here. This one. This is a PR which kind of, at first I wasn't sure it would be possible or not. But it kind of reads like exactly what I want to do, except for a completely different implementation. So codec HTTP2 couples the dependency tree state with the remainder of the stream state. This makes implementing constraints where the stream state and the dependency tree state diverge in the RFC challenging. For example, the RFC recommends retaining dependency tree state after a stream transitions to closed. Dependency tree state can be exchanged on streams and idle. In practice, clients may use stream IDs for the purpose of establishing quality of service classes, and therefore retaining this dependency tree state can be important to client perceived performance. It is difficult to limit the total amount of state we retain when stream state and dependency tree state is combined. It's basically like exactly the problem I'm having. It's pretty funny to read it just like that on some other PR. So obviously I can't just merge this because it's Java, which is like really unfortunate. Or I don't know, maybe it's fortunate. But I have to try at least doing the same transform to my own code. So what I have is this exactly the same, almost exactly the same situation as them before they made that PR. I have this class called stream, and it basically, I don't know if I was thinking ahead, but it includes this module called flow control, which basically implements all the flow control logic. Now, I don't know how hard it's going to be to split this apart. This code is pretty nuanced, and yeah, I don't think this is going to be that fun or that exciting, but it will be good because it will mean that once a stream enters the closed state, I will be able to just toss it away, and all the state that's associated with that stream will be garbage collected, which is exactly the opposite of the problem I have right now. I wonder if I have this. I can show you. I don't really have an example just sitting in a terminal over here at the moment, but it was easy for the Falcon proxy to churn through, I don't know, like a gigabyte of stuff, just because it was retaining all those streams. And I you know, it's okay, I guess, in a way, because this implementation is pretty young. And in a way, like, I expected things like this to crop up, and it was more a matter of just let's make it work and then let's make it fast. so it works, and now let's make it not use hundreds or gigabytes of memory. So the first thing I want to do is I want to take all of the stream, I want to split the stream code up. And I really don't know how successful this is going to be, but at least it might work. I don't know. It's a little bit scary. There's just so much stuff in here. I don't actually know if the windows need to be stored in the stream or in the dependency tree. It might be better to put them in the stream, or the problem is the stream window actually, my understanding is it impacts dependent streams. So if you have a parent stream and that has 3 children streams, the parent stream window will also control how much data the children get. So it probably needs to be separate. So let's just get rid of all of that, and let's call this dependency. We're still going to include flow control, but we're going to get rid of that over here. And I guess what we want to do with this is we just want to when the stream, because the stream will probably exist for a shorter time, a subset of the time that the dependency node exists for, and so we can probably just steal the windows from the dependency object, while the stream is in existence, because we obviously don't want to make the bandwidth allocation calculations complicated, more complicated. Right, so I kind of feel that some elements of HTTP2 just made things way too complicated. From a point of view that you want to keep things reliable, simple, but HTTP2 just is not simple. And I guess HTTP3 makes it even, I don't know, it's like Google is just, I wish they solved it in the protocol layer, like a new version of TCP or something that just meant that multiplexing wasn't so bad. Okay, so none of that stuff is necessary. That's not necessary. State still necessary. That's not necessary. None of that's necessary. That's probably not necessary. I think this refactoring will ultimately be good because it probably keeps the stream state a lot simpler. And all I did today was I went on, worked on my house. I'm doing some renovations on my house, and I just stepped away from the code and just thought about it for a while. What is it that I want to do? Like, how do I want to fix this problem, basically? Because what I was planning on doing, you see I've made a few changes around here, just playing around with it. I was thinking of when the stream changes into this closed state, set all the resources to nil so that the garbage collector can go and clean it up. So what I have been playing around with, awesome, is so here's an example. This is the HTTP2 implementation that's used by Falcon. So when you call close on a stream, it sets the request to nil, so that the stream won't retain the request, so that the connection that retains the stream in the closed state will not retain or cause the state to be retained. So that's kind of one way of solving this problem. But what I found was when I did this, other code actually broke because it depended on being able to pick up some of this state, like even after a stream was finished. Like, so I had a reference to the stream. It was like, well, I want to check the request, or or in the case of response, there was a bit of other state. Where is it? So response has a list of promises. And then finally there was this generic. This is a shared base for those two things. It also has some extra handling of what to do. So there's a whole bunch of state. I think, oh no, hold on, it's the wrong one. This one. Right, so it sets headers to nil, trailers to nil. The input and output streams, they all will get dealt with. So there's a whole bunch of like logic, what happens when a stream transitions to the closed state. And that wasn't like that before. So, I mean, even after the stream was transitioned to closed, you could still pull out the headers. And I think that's a valid use case. I think even though the stream is closed, you should have to pull state out of it. But the thing is, the connection shouldn't retain that stream after the stream is closed, because otherwise you just have this hash table that just will grow forever, which is a disaster, really. Right, let's jump back to the code. So this is a directed tree. Actually, all trees are directed, I guess. A directed acyclic graph. It's just a tree that has a connection at the very root, and it has a list of children. And I wonder if I should make... I think I can be a little bit more opinionated now that I'm sort of detaching this stuff. Because like that PR said, when a stream is idle, it also kind of doesn't exist. There's no point in tracking the state of an idle stream. But you do need to be able to change its priority. So even though a stream might not be doing anything, it still plays a part in flow control. So we don't need to create a stream object for it, just it needs to sit in that tree of flow control. So there is some priority stuff, and I'm not quite sure if I need to keep that or not, but I guess we'll find out. I wonder if I have to still do that. This is kind of the nightmare of this, just how HP is so complicated. There's so much stuff that I've written here which has come from RFCs. So I've been reading an RFC and basically translating it into code. And now I'm just like, do I need that line of code? Like, how does that fit in? At least with HTTP2, it was kind of, with HTTP1, it was kind of intuitive, I will say. But with this, it's just a mystery. Maybe I'm just not used to it, I don't know. So this is our dependency tree, and this is our streams. And actually, maybe I wonder if it needs to be a hash table or not. I guess we'll find out. It might just be sufficient to be an array. Right, so the first thing I want to do is when a stream is being closed, we are going to delete it from the connection because that's like the number one thing I wanted to achieve. If I could just do that and all the specs passed, then I'm finished. I don't think they're going to pass, but maybe if I'm really lucky. I don't have that anyway. Okay. There was a really interesting thing that I had to work around this because that streams hash table can contain closed streams. It was necessary to have sort of an active or like an active counter so that we know how many streams actually, without having to like just walk through them all, how many streams are active, because in HTTP2 there's a configuration or setting which lets you limit the number of active streams, and you need to like check that so you can say, well, you're trying to make too many streams. But now this just becomes streams.size, because the only streams that are going to be in that list are the ones that are active. Actually, am I just making it an over? Is it? I guess I'll just do this for now. By the way, I don't think I'm going to finish this in one video, and I probably won't stream all of it because it's probably not that exciting. Okay, so when a stream enters the closed state, we're going to delete it from the connection. There's like my number one thing that I wanted to do. And the next thing I wanted to do was I think it's only used in like one place. So let's just get rid of that. It's not really necessary anymore. Now, the connection exists forever, and it implements this interface because this is the flow control. And let's have a look at flow control because it's kind of the interesting thing. So this module called flow control manages the read and write windows. So window is basically the number of bytes that the remote end is expecting to receive, or that you are expecting to receive. And the reason why windows are useful is because there's a term called back pressure, which means when you write to the network, you don't want to write more data than the remote end can receive, because you'll stop if you have the first thing that comes into my mind is like, someone holding a pile of books, and if you just give them too many books, eventually the whole lot will just collapse. Same thing happens in a network. If you try and put too many packets into the network, it will start dropping them. So there's lots of different ways of dealing with that, but the idea of flow control is just a mechanism for figuring out when someone is going to start dropping packets. And the way this works is, when you make a connection in HTTP2, the remote end says, I would like a maximum of 32 kilobytes. And when you send it 32 kilobytes, it will come back to you when it's ready and say, I'd like another 32 kilobytes. And provided you do that in a timely fashion, it doesn't slow the connection down, but the end-to-end latency will dictate how quickly those flow control windows are updated. But yeah, it's super complicated to do it at the application layer. So this is the main function here, consume window. What it basically does is it goes through all the streams for each node in the tree. It sorts the children by the weight that it's been assigned, and then it goes through each of those children in that order. It calculates the allocated window, which is child.weight times size divided by total. So a weight might be like 16, and I guess size should be the data available, and total is the maximum, the sum of all weights. So this just basically computes like a proportional amount of bytes. And then it says to the child, you can consume your window now this much. And then that stream, like it could be a JSON response, sends that many bytes of the response. I don't know if a lot of this code will need to change, but I don't know how much of this code. This is more tricky. It's like a stream, but it's not a stream. So it doesn't have a state. But all the rest of it still exists. And I guess that kind of annoys me a little bit, because now we have to make two allocations per stream, per stream, I guess. One for managing the flow control and one for the stream state itself, and we're going to jump between the two when we're processing, telling it to send data or whatever. The stream will have to ask the flow control state, how much data can I send? I guess it could be a nice separation of concerns, but I don't know. Maybe it's good. I do like separating out code. It just makes it easy to understand. It's like when you bake a pie and you put too many things in it. Individually, they might all be good, but like when you start mixing them together, it's not good. This was partly made to try and deal with the mess of the connection not knowing what kind of stream would let me try and explain it this way. A stream represents the state of a specific request or response. So it's nice to subclass stream to capture all the things that are related to a specific request or response, like your own application state, for example. Now, I'm not saying this is something you do in a Rack application, but it's something Falcon and async HTTP use to keep track of what's going on, how to generate data for a stream, and so on. Push promises, for example, need to know, what stream to deal with. So when you first set the dependency and priority for a stream, that stream just uses this generic class called stream. But then when you finally end up creating the stream, like the request or the response, you might actually have a custom subclass of stream. And so there was this replace method. And what this replace method does is it says, make an instance of the class that you're calling, it could be like my custom stream.replace. And it kind of builds the state of that class from the state of the existing idle stream, which is just this generic class. And to be honest, it's kind of a mess, actually, now I think about it. And so it can be done better because that state is kept separate in the dependency tree. So I don't think we strictly need this, but I want to find out where it's used, because maybe we can just make it a no-op. I thought it was used over there. Oh, I guess we can just delete it for now, because now the stream won't be created in the idle state. Okay, it was in here. So this method here multiplexes between the two, create or replace. You go, I am accepting an incoming stream, this connection, this ID, and obviously self is the class that you want to use for the stream. And if there was an existing stream, then it calls replace, otherwise it calls create. But now, so those methods can go, I think. Let's just shove that over there. And this code is going to be a little bit simpler, I guess, because what we're going to do is we're going to go, we still have this sort of conditional execution but it's not to do with the stream, it's to do with the dependency node and the dependency tree. So we're always going to create a new connection for ourselves, which was essentially that. And we could probably leave it at that, because we can do a lazy lookup of the dependency state of the flow control stuff, and we can get rid of that because it's always going to be active. It's never going to be idle. States still start off in the idle. The stream still starts off in the idle state, but we will deal with that in a bit. Oh, shit. Excuse me. So I don't know if we need to hold on to local and remote window, because that's just going to be dealt with elsewhere. We might need to add accesses if there's too much code that depends on it. So there is no super implementation to call. what we need now is a way to look up. And maybe calling it dependency is a really bad name. Flow control. Do we have anything called dependency in here? We do have dependent ID. It's a little bit confusing. Oh, I guess we can just rename it if it gets super confusing. Dependency. So this is going to be dependency. It makes more sense to call it flow control. That makes more sense to me. Okay, right. Self-flow control, let's change the name of that method up here. And that's, is it going to be difficult to find the flow control node? Let's just lazily initialize it. Right, okay, I'm happy with that. This could be tricky. Flow controls, plural. I don't want to end up in a situation where I have to retain each state there as well, but I guess we'll find out. I mean, every stream does need a set of windows, so okay, so this is where we're going to create the dependency if necessary. That's actually a little bit nicer because there's less levels of indirection. I'm pretty happy with it. Fetch or create okay, that looks okay. That looks okay. Update local window. I don't think we're going to put any priority handling on streams. I think it's going to go through the dependency node tree. Now there's one more bit which is important. So this is the critical point in the flow control management where when you say I want to write some data, essentially what it does is it says this is the maximum frame size that I can use for this stream. But that's different. Actually, hold on, what am I talking about? There is actually a maximum frame size. It's taken into account already, but this available frame size takes into account the window. So it says until the chunk is empty, figure out the maximum size. If the maximum size is less than or equal to 0, which is possible with HTTP2, it can have negative flow control windows, in which case you just got to wait, which is literally what it does there. Until the window is updated, it will wait. And then it computes the new maximum frame size in a loop, so it will just keep on waiting until it becomes positive. And then finally it will basically call send data, chunk, and maximum size. I'm guessing send data truncates it and returns the outstanding amount. But anyway, so available frame size, it used to be on the stream, and I mean it still is on the stream, but it now needs to defer to it would have been part of that flow control module. And so now stream. Connection available frame size, because there's a set of flow control windows per stream, and there's also a set of flow control windows for the whole connection. and so obviously you can't send more data than what their connection will allow, and then also that a specific stream will allow. So that's why we don't send more than the maximum frame size of the connection. And to be honest, maybe I can just put that straight into there. Okay. So the next thing that we have to deal with is how to send or allocate data in the idle background loop of the HTTP2 connection. So this thing called read in background, and this will have to change, well, this won't have to change, but how it works internally will change a little bit. It's a background task that continuously reads frames from the underlying connection and applies them to the connection or stream as required. And this method consume window is really critical because what this does is it basically goes through all the streams and allocates and says, please, you have an opportunity to write data. If a frame comes in that says there's a window available, you need to divvy it up somehow. So that's going to be exciting. Right, so this is the callback, essentially. As it traverses the tree of dependencies and figures out data that can be applied to each stream, it calls window updated where possible. And this returns whether the window was used or not. Now, this method now needs to trigger So in async HTTP, window updated is actually just hitting a notification or something, and that is triggering the output. But it is true that a stream actually outlives, sorry, a dependency node in the dependency tree actually outlives the stream. The stream should exist for a shorter period of time, I guess. So shouldn't the dependency know about its stream so it can say the flow control one? Yeah, I don't know. Shouldn't. So what I should be doing in here is so if the stream exists, then tell it the window is updated. Otherwise, return false. Otherwise, return what the window update returned. That seems to make sense. Let's try running some specs. It's probably not going to work, but awesome. Connection 384 create stream. I'm not going to bother doing that lazily. Because it actually has the side effect of pulling the data from the settings, which is the initial window sizes. And I don't want to risk that doing it at the wrong time. It was just one place. Oh yeah, that looks okay. So that will create the dependency in this in the stream. Flow control for flow controls. What did I call it? It might help if it was available. And it should pull in flow control. Okay, good. Activate stream 206 open. cannot receive data for stream RD1. Okay. Can create new stream and send response. Connection spec 82. Okay, let's have a look. Connection spec 82. Okay, client creates stream send headers. Expect server.streams to not be empty. Yeah, I think I'm not inserting it, but I should be. That's what that code did. Wrong number of arguments given, one expected 0. Okay, so it takes a frame, which is the frame that updated the flow control window. Undefined method remote window for protocol. Okay. So we'll just expose those. Okay, a whole bunch of stuff is passing. Undefined method parent equals stream. Push promises, just speaking without thinking, have to be just, I don't know, one of the most ridiculous features I have encountered in HTTP2. Let me qualify it by saying that. If you are a client, the only time push promises are useful is when you're doing your first request and you have nothing. And at almost every point after that, you'll have some kind of cache, like a local private cache or something. So it just seems like 99% of the time, the push promise is just wasting resources. I mean, how much latency does it save? On a real network, I just can't imagine it saves a huge amount. Right, 420, stream.parent equals self. What is this doing? Why is it doing it? Right, I see. And what is self? Self is another stream. So we can emulate that API because it's actually not that stupid. And what we actually mean is flow control parent equals, and I think I'm going to change name flow control to something else because this just doesn't make any sense to me anymore. But anyway, we'll just keep it as that for now. think that should work because that has the parent stuff. I don't know if any of that stuff still works, but I guess we'll find out. That makes slightly more sense. Stream priority, no, okay. I don't even know if dependency is better, but who cares? I'll think of it more some other time. Oh, awesome, I can't assign a priority. Oh, 432. So this is an interesting one. This is actually a method I gotta fix. So this was one of these weird things, where the stream doesn't exist yet, so we have to create it because we've just received a priority information for it. But actually, we don't want to create a stream now because it will just sit in the idle state and it's just wasting resources and it's not really serving any purpose. So what we want to do in here is we want to go stream equals dependencies frame stream ID, and it's not, it's dependency, then dependency receive priority, otherwise dependency for frame stream ID. In fact, we can just do that right at the top because it already does that on demand thing, and that bit there. And I feel that that code is a lot more elegant than before. Undefined wait for nil class. Okay, so set the priority and then it can't get the wait because of course the stream doesn't exist yet, which is exactly what we wanted. Let's duplicate that and make a dependency spec. Let's come in here and get rid of whatever is on line 31. Oh wow, this is just all stuff that I don't care about here anymore. Okay, I don't like rewriting specs very much. Okay, we create a stream, we get the priority of the stream, there should be a default, that makes sense. And it died on line 43, which was that one. Server dependency stream ID. Should be 32, that makes sense. I need to make sure there is an accessor. How's that spec even working? What is server? Should send window update after exhausting half of the available window. So this is, there's a variety of techniques you can use to deal with updating the window. So like the worst possible one is that you don't update the window until the remote end is exhausted, all of it, and then you'll have like a full round trip latency before the remote end can actually start reading any more data, because you'll be like, okay, you want 100 bytes of data, and the remote end goes, okay, like I'll receive 100 bytes, and then so you send 100 bytes and your window is now 0. And then the remote end is like, well, I can't do anything now because there's no window, and so you're like, okay, I'll send, I'll increase your window by, I don't know, 100 bytes or something. And if you just wait until there's nothing left, then you're just basically going to wait until the window is updated until you can do anything. So you want to update the window before you run out of window. And so one of the techniques is, I've got it in this implementation, when your window gets half the size of what it was originally, it will then request more data, and it will increase the window size. But there's different techniques. Undefined method write frame, send window update. Oh, that makes sense. So this is actually a little bit more exciting than I imagined. It's trying to write a frame, and before it was going through the stream, which was just calling connection write frame. So we'll flick that out through the connection directly. It should be okay. Undefined method received, window update, connection 452. Else if Receive window update. Receiving any frame other than headers a priority on a stream, and the state must be treated as a connection error type protocol. Okay, so I guess what we want is dependency equals that, because we don't want to just create it if it doesn't exist yet, because we have to sending reset stream, which is probably mandated by the RFC in this case, is actually something which just changes the state of the stream. And so we probably just want to do this on the stream and have it flick it through to the dependency. It might just be easier. What was it before? It was that. Oh, awesome. Look at that. Everything's awesome. Oh no. Awesome. Okay, add child dependency process priority. Undefined method delete for nil class dependency 79. It might not have children, that's okay, so don't try and delete them. Dependency spec line 60. Oh, all these specs have to change. Okay, let's have a look. Create streams, commit 4 streams. We do some priority manipulations. And then I think that should be correct. Yeah, so I think that this is not creating the dependencies quite right. Create stream. Stream accept. That should have been working. So we've got 4 streams, a I wonder if I should just make those methods work. It's kind of a mash up of state though. Children is dependency children map. Map them back to streams again. Like I said, I don't really like changing specs that much. And it's, I think I should turn it back into a hash table. Children is not available. Oh, whoops. Unified method stream. Okay. How do you map a hash? Does it turn back into a hash? No. Okay. Why is that no? Okay, I see what's happening. This is making 4 streams on the client. Then it is manipulating the priority, which sends those priority frames from the client to the server. Then I'm telling the server read 1 frame and then see what happens. And then it's testing what's changed on the server. Well, this is the client side state and this is the server side state. So because the stream is still idle, it doesn't exist on the server. Great. Now we're down to here. So it's just the structure of the code changed a little bit. Receive priority stream spec. I see what it was testing. On a closed stream, you should still be able to handle changes to priority. But that doesn't really make any sense anymore, that spec. Because it doesn't matter where the stream is closed. It will still get processed because it's now through this other thing. Excellent. So I think I'm going to leave it there for now. It's been a pretty interesting change. I didn't know how complicated it was going to be. Like, frankly speaking, there's so much code involved that it's quite easy to sort of jump from one place to another. And I haven't really looked at this code for quite a while, but I'm lucky that I wrote a lot of specs. It gives me a lot of confidence that it's going to work in production later today, of course. So I am happy that all the specs are passing. That doesn't mean it's going to work in async HTTP, which has got plenty more specs. This is really just the protocol layer itself in this gem. And then async HTTP depends on a lot of the behavior of those prioritizations and weightings, and obviously the fact that everything has to fit together and work. And then finally, even if that all works, that doesn't guarantee that a browser like Chrome or like Internet Explorer or Firefox, those browsers are again with their own implementation of HTTP2 sometimes do strange things, or my implementation is wrong. It seems to work in isolation when I'm testing internally. For example, async HTTP client and server might work fine together, but because there's a bug, there's a bug in the client, but there's also a bug in the server that means that it's not obvious. When you try a real web browser, things go to custard, and not the good kind. So finally stick it into Falcon, put it in production, and hit some web browsers against it. It would actually be nice to automate that somewhat. Async HTTP as a server, if you could spin up an instance in the test maybe, and then use Capybara or something to hit it with a real web server and see if the protocol is actually working correctly. But yeah, I'm really happy with this. This is really good progress. It means that the streams won't retain state, which should improve the memory usage of the implementation quite a bit. And that should probably be one of the last things necessary to get this running in production without Nginx. So we'll see how we go tonight. I'll let you know on Twitter. Excellent.